Hi, folks. We have been talking about matter. Now, matter is stuff, all the wonderful and delightful types of stuff that are out there. Now, can you imagine what it was like for early chemists as they tried to figure out what all stuff, all matter is made out of? Everything from kittens to planets to the sky, table salt, people, plants, whatever. And they said, all of the stuff that's out there, what is it made out of? There was so many different kinds of things, and they wanted to organize it into different types. Well, human beings, when we are overwhelmed, when we have just lots and lots of data and we have to make sense out of it, we have a tendency to categorize it. We decide to put it in lots of different piles. And whether you're talking about clothes to sort or people you have to date, you have a tendency to put them in different categories. Guys who have pickup trucks, girls that like Chinese food, people who like sci-fi movies. Hey, we do that. So you classify in order to simplify an overabundance of information. And that's what chemists did with matter. With matter, they took all of the different kinds of stuff that was out there in the universe and they said, okay, first thing we're going to do is ask this question. Can the matter be separated physically or can it not be separated physically? Meaning, can it be separated by picking it up and putting it in different piles? Or if you go this direction, must you have a chemical reaction in order to break it apart? So we're going to start by talking about things that can be separated physically, and those are going to be called mixtures. And that is really the definition of a mixture. A mixture is a physical combination of matter, and it can be in any proportion. The properties of the physical mixture are the combination of the properties of the substances in the mixture. Here are a few examples, and I think the best example is the salad. You've got tomatoes and cucumbers and lettuce, and each maintains its unique properties, but they're all mixed, matched together. Gravel is another great example of mixtures. Each rock is unique, but they're all together. Now you start getting something like Kool-Aid. Well, Kool-Aid is different because it's hard to separate the pieces out, but you can if you were really careful. Kool-Aid is a mixture of the Kool-Aid powder and water and sugar. But when you take a sip, you take a drink of this, you get some of each one of these in each sip, and that gives you that lovely flavor of Kool-Aid. Shampoo, body wash, hand lotion, things like that, they are a mixture of creams. Sometimes they include some soap, sometimes they include some fragrance, and they are all mixed together to give us the combination of properties we want. Now remember, mixtures can be separated by physical means. What do I mean by physical means? That means that no new molecules are produced in the process and there's no chemical reaction involved. So let's talk about how you can separate things physically. One of the most common ways we do this, I like to call pick and pile. You pick it up and you put it in a different pile. Every time you sort laundry, that's what you're going to do. If you separate the veggies on your plate, the peas from the carrots from the corn, you're putting it in different piles. Another method that's commonly used is we use some sort of a filter or a sieve. Well, if you have pasta and water, you put it through the colander, the water goes out, the pasta stays. You have water and coffee grounds, the coffee molecules, the lovely flavorings, and caffeine goes through, but the grounds stay behind. You can separate gravel by the sand goes through and the big rocks stay on top. So filters are used often. Sometimes heat is used to separate a mixture. Think about what your clothes dryer actually does. You have a mixture of clothes plus water. And your hair dryer, you have hair plus water. And in both situations, you add heat. and the purpose of the heat is to remove the water, keep the hair, keep the clothes. Sometimes we separate things by differences in density. The light things float to the top, the heavy things sink to the bottom. And now and then, we use speed at which an object moves through material to separate a mixture. So let's talk about some chemistry applications of this. In a chem lab, we might use filtration. It's just like your coffee filter. We have a piece of filter paper. You pour a mixture through, the solids stay up here, and the liquids pour through. Drying, we might have a liquid and a solid, and the liquids evaporate away, and we maintain those solids. Remember I talked about that foot race? Different things move at different speeds. That's how it works in chromatography. Chromos means color. Graphy means picture. So you get a color picture of what is inside of something. These happen to be different inks or dyes. And a liquid wicks up through this piece of paper. Different inks or dyes are on it, and they separate because big molecules move slowly, light molecules move more quickly. Electrophoresis, this is how DNA samples are separated. And the DNA is put on a gel, an electric current is placed through it to make the strands separate out into different pieces. And that's how a DNA strand can be separated, and you get a unique DNA profile for each person. Something as simple as a magnet can be used in a lab. Iron filings will be attracted, and non-metallic things like this yellow sulfur will not be. Distillation is used in lab, and distillation is very often used when we have two or more liquids that we need to separate. Commonly, it's used when you have water and alcohol, and they're both clear liquids. How do you separate two clear liquids from each other? That's kind of tricky. Well, we use their boiling point because we can heat them very carefully, and one's going to turn into a gas before the other. So there's lots of ways of doing this in a laboratory. Now, there are two different general categories of mixtures: homogeneous mixtures and heterogeneous mixtures. Now, homogeneous mixtures or homogeneous mixtures, both are correct pronunciations. Homogeneous mixtures and heterogeneous, listen carefully. Here's an ear here. Listen carefully to the words, and I'm going to ask you the question. Which of these two is going to represent a situation where all samples are going to be pretty much the same? If you have a homogeneous mixture or a heterogeneous mixture, all samples are going to be pretty much the same. Which kind of mixture is that going to be? Well, that's going to be a homogeneous mixture, like homogenized milk. Every sample is the same. A heterogeneous mixture, every sample could be different. So let's look at some examples. Homogeneous versus heterogeneous mixtures. Kool-Aid, that's probably going to be pretty homogeneous. Unless you get way down to the bottom and it wasn't mixed well, then you're going to get a lot of sugar. Then it's probably a little heterogeneous. Okay, what I'm going to ask you to do is hit pause, take 10 seconds, identify each one of these, take your best guess, homogeneous or heterogeneous, then we're going to come back and go through them. Okay, are you done? All right, let's try this. Salad, what do you think? Oh yeah, that's heterogeneous for sure. Gravel, heterogeneous. One sample of rock or gravel is going to be very different from the next sample of gravel. Black coffee? Oh yeah, black coffee, homogeneous. One sip should be the same as the next. Now, somebody out there is saying, what about the dregs on the bottom that's got that little brown gooky stuff? Okay, you get down there, yeah, then it's probably a little heterogeneous. Granola. Granola is probably heterogeneous. Why? Because sometimes you're going to get more raisins and sometimes you're not. Blood? Blood's going to be pretty homogeneous. 1 milliliter of whole blood is going to be a lot like the next milliliter of whole blood from the same person. Vinegar and oil salad dressing, perfect example of a heterogeneous mixture. This separates out by density, oil on top, vinegar, and you get all these lovely solids sinking to the bottom. Now, I've been dancing around milk, and I love dancing around milk here because it says right on the carton, homogenated milk. But what is homogenated? It is a homogeneous mixture. Well, most of us have bought skim milk, 2% milk, and 1% milk, and whole milk. Well, what's going on here? It's the percent butter fat. We're talking about the percent butter fat that is in the milk. Those of you who've grown up on a farm know that if you get the milk right out of the bulk tank, the butter fat is the lovely creamy stuff on top, and then you get the skim milk down below. When our son was little, we'd go down to the neighbors, get milk right out of the bulk tank, bring it home, shake the heck out of it before pouring it on the cereal to mix it all up. Otherwise, the first bit was really good because it was all the butter fat, and then the rest of it wasn't so good because it was skim milk and still not my favorite. So these percentages, 2%, 1%, skim is none, whole milk is about 4%, and that's how much butter fat is in the milk. And it has been shook up really well to make one sip of milk the same or homogeneous compared to the next sip of milk. So all the matter in the world, chemists looked at it and said, if we can separate it physically, we're going to call it a mixture. If we cannot separate it physically, then we're going to call it something else. And in the next video, we're going to talk about that something else. See you later. Bye-bye.